that. And how do you take derivative of two functions that are being subtracted? Just do them separately, right? So isn't the derivative of w at c equal to the derivative of a at c minus the derivative of b at c? Right? And doesn't that have to be equal to 0? Yes? Move that to that side. Done. Right? 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 Didn't we just conclude that the speed of the A car at some point in time must be equal to the speed of the B car at some point in time? Okay, there's no debating anymore. There is a point in time where they both must reach some speed, and it must be at the exact same moment in time. If they start and end at the same time, it has to happen. It's kind of an interesting sort of approach to that, isn't it? Okay, so hopefully that convinces you that these theorems where we do these little things and we're like, okay, you know, what would we ever need that for? You can see here, like, this is an example of where you take your rationale, you know, and you can kind of throw it out the window. Because sometimes your instinct is wrong, right? And you don't want to build a bridge with the wrong instinct. Or a plane.
The speed
Yes.
that they hit at the same time
Yes.
doesn't have to be like
Their average speed.
Yeah, it can just be any speed.
Well, that's the third question.
Yeah, like,
Is that speed that they both must reach the average speed?
I don't know that.
You doubt it? Yeah. I don't know.
I mean, if
I
it's
haven't
your
thought about
average
that.
Speed, then you have to hit it at some point, right?
So
If that's the only speed that that's
here's I think a way we can resolve that pretty easily is by drawing two very extreme curves. So the car that goes and starts off very fast and does that, and then do the car that goes really slow, like this, and then goes like that. I think if you do it that way, here's the secant line. Like this one, this black curve hits its average speed like somewhere around in here, right? And this one definitely does not hit its average speed. It hits like here. I said same speed, yep. So the first question is there a speed that they both must see? At some point in time, different times maybe, they both have to see the same speed. Yes, their average speed would be an example of that. This guy's got to see his average speed right here. This guy's going to see his average speed right here. But there's even more than that. There's a speed, not their average speed, but there is some speed that they both must see on their speedometers at the exact same moment in time. And it's hard from those pictures to figure out where it is, but it's there. It's somewhere. And it has nothing to do with this anymore, right? It's somewhere where these two, because you can see the tangent lines are like this, right? Somewhere in there, they're going to be, right? But they have to be exactly at the same moment. So, yeah, all right, it is what it is. So on this same sort of topic, you know, before I move into the next section, I have a lot of friends that are engineers. I have a lot of friends that are in the STEM field. And when we get together, I always talk to them about, you know, what is it that I need to tell my calculus students about, you know, what it is that they need moving forward? Like, what does an engineer need? Do they need to be able to do this? No, right? It's about problem solving. It's about critical thinking, okay? So to give you an example of this, I'm going to tell you about an interview that my brother had. My brother is an electrical engineer, first job he ever got out of college. He went to a job interview. And they asked him a couple of questions, but two questions in particular that stand out, okay? So the first question was, this is like a legit face-to-face interview. You don't have time to go home and work this out, okay? So the first one was, you have 10 coins, all right, 10 coins. They all look identical, but one of the 10 coins is just slightly heavier than the other 9. So you've got 9 identical coins, same weight, a 10th coin that is a little heavier, and you have a balance. Okay? You have a balance, one of those little scale balances. Okay? What is the minimum number of weighings, or, so if I put 2 coins on here, well, that's going to count as being a weighing, right? What's the minimum number of weighings that are required to guarantee find that heaviest coin? So that's the question. What do you got?
3, right?
Well, that was the question. So 3. Anyone else? 5. So you got to do it with 3.
Yeah.
We'll go with yours. So how would you do it?
Okay, so it would be...
4, 5, 6, 7, 8, 9. There's your 10 coins.
So initially when I thought 3, it was like, well, if you get lucky and pick up a lightning.
So you could just get lucky, right? Like you could just like pick 2, go like that, compare them, and then boop, one side goes down, you like got it in 1.
Yeah.
But the question is the minimum number of weighings to guarantee you're going to find it.
Well, then you could, I was thinking 3, because then if you have 2 uneven coins, right, then you could weigh each of those uneven coins against a different coin.
So you're saying 3. Tell me how to do it then.
Well, that's if you get lucky, you can do it. What?
What do you think?
So you would do 5.
Are you sticking with 3?
I'm sticking with 3.
Yeah.
You're sticking with 3, so what would you do?
5 on one side.
5 on one side, 5 on the other.
The heavier side
Heavier side's going to go down.
would go down.
Okay.
Take the less side.
Okay, so let's do that. So the first weighing was 5 and 5. So 5 here, 5 here. One side goes down. Let's say this side goes down. What do you do?
Then you split it up 2 and 2, and then
Okay.
you take one back and one out.
So you're going to now, on the second one, you're taking those, and you're going to go 2 here and 2 here. And then you got 1 coin sitting over here, right? Okay, so what now?
But then now, if one of them goes down, then it's in there, and the third weighing would be on those 2. And if they're the same, then that coin that they left out is the one that's...
Yeah, so if this balances, you got lucky, and there's your heavier coin, right? If this doesn't balance, right, one side's going to go down. Let's say it's that side goes down. Then it's got to be in here, right? So you do a third weighing of just those 2. And of course, one side's going to go down. The minimum is 3. 5 and 5, 2 and 2, 1 on the side. That's the answer they wanted. Good. You're hired. No, you have to get the second question. So the second question, you have to pay attention to this one, all right? Because the wording of this is super important, all right? And the answer is debatable, but not really, because this is an electrical engineering job, okay? You ready? Here it comes. 2 archaeologists stumble upon a cave. One of them goes inside, comes back out, tells the other archaeologist, I just found the perfectly preserved remains of the first human being. The question is, how did he know he had found the first human being? That's the interview question. I'll say it again. 2 archaeologists stumble upon a cave. One of them goes inside, comes back out, tells the other archaeologist, I just found the perfectly preserved remains of the first human being. How did he know he had found the first human being? So if you have an answer, don't blurt it out. And raise your hand, Noah. But your job is in the balance here. These are not the type of questions you would expect in an electrical engineering interview. You got an answer? You ready? You think so? Go for it.
Are they like the only 3 people alive? Like the one person that they found the remains of?
No? Maybe I don't understand what you're saying.
Like they're the only 3 people on Earth, and then one person died, and they found the remains.
I don't think the question wanted that sort of, yeah. No, okay, I mean, you're thinking about something, right? Anyone else? Should I state it again or no?
Is he lying?
Is he lying? No, he's not lying. 2 archaeologists stumble upon a cave. One of them goes inside, comes back out, tells the other one, I just found the perfectly preserved remains of the first human being. How did he know?
Is there a trick in the question?
There's no trick.
It's
It's whatever you want it to be. So I'll give you a hint if you want a hint. Okay, perfectly preserved remains is a huge part of this.
Oh, like remains, but
The perfectly preserved remains of the first human being is what he found. What do you got?
How would the first human being like have that kind of capacity to like?
Well, maybe it's frozen or something. I don't know. It's perfectly preserved, whatever. Yes.
It's remains.
The remains, like the body. Yeah. I'm phrasing it the way it was phrased to him. So I mean, yeah. Okay. Y'all ready? We don't have all day. We're going to move on to the next applicant. I'm just kidding. That is one of the debated ones. So, okay, so you need to elaborate on that then.
Well, like,
If you're going to go that route,
Oh, I'm just like throwing like, are you asking for a purely scientific answer?
I'm not asking for anything. I'm telling you the question they asked my brother. Okay, you ready for the answer?
Yeah.
Okay. Perfectly preserved remains, right? Human being didn't have a belly button. The body that was laying there didn't have a belly button. That's the answer they wanted. Right? To be born, you have to be born, you have to have an umbilical cord, right? If you're the first human, then you cannot have been born.
Well, then it depends on.
Listen, okay, so the other answer that I think is within maybe reason would be like missing a rib, but that's more like Adam Eve type thing. Whatever. Okay, look, the answer they wanted was no belly button.
Did he say that?
He got it, yeah. Yeah, he got it, yeah. Yeah. So that's a way of thinking. That's a way of thinking, and that's what they're looking for, is a way of thinking about things. It's not necessarily can you do calculus 2 or 3, or it's have you trained your brain to think a certain way, because you know all my brother does for a living is solves problems. That's all he does. He solves problems. You know? And if your way of thinking is where's the solution manual, or let me go to YouTube or Google to find answers, you're never training your brain to think critically. And that's what they want. They want critical thinkers. And it's hard to develop. That's what college is about. It's not necessarily about the classes. It's about you developing your brain to the point where you start thinking like that. Like, just, that's the answer that came out, you know? There's another one. I'm not going to spend any time on it because I don't have time. They gave him well, no, they didn't give him. I gave him this problem because I wanted to see if I could stump him. So I gave him, I've got these sticks, right, or sticks, whatever, they're all the same length. Lay them down on a sheet of paper, or you lay them down on the table, and you say, okay, you've got what, 1, 2, 3, 4, 5, 6 sticks, right? What's that?
Make a square.
No, the thing is, what you have to do is, you can move those sticks however you want. You need to create from that 4 equilateral triangles. So right now, you see 2 equilateral triangles. You need to create 4 of them. And they all have to have this length as the length of each equilateral triangle. So, yeah, you can move them around. You can do whatever you want. You can move them around so you can start, you know, messing with these. Yeah? So I gave that to my brother, and he couldn't get it. He gave up after a few days. So the answer to this, I don't know if y'all can see my table, all right? But the answer to this is this. Is a pyramid. And see, the thing is, when you give the problem, you put everything on a table, and everybody just goes right into 2 dimensions. And they try and do everything down here, and they don't think outside in 3-dimensional space. Some people get it. I've seen people get it pretty quick, but it's just, again, how does your brain process information, right? All right, we are way off topic. That's okay. Yeah, my job interview was I just had to solve math problems. That was pretty easy. All right. Derivatives in the shapes of graphs. Moving into the next section. We're supposed to do a quiz here soon, aren't we? We can get through the beginning of this. There's a lot of notes here. These are all on Canvas. Don't go sit and try and copy all this down. The beginning is just some definitions, all right? And we've already talked about this a little bit. If we look at a function and we look at its derivative, the function having a positive derivative should mean that the function is going up, right? And if the function has a negative derivative, the function then is going down. And if the derivative is 0, then it should be flat. So this is just an illustration. This function right here is increasing. Would you all agree as we read it from left to right? The function goes up, right? It's from left to right. So if we look at the derivative at every moment, at every point, notice that the slope of the tangent line is always positive, right? So there's a major correlation between the derivative and the shape of this graph. If the derivative is positive all the time, we know the function goes up the whole time, right? On the other hand, if the function is going down all the time, then the derivative is always going to be negative. And if the derivative is always 0, then we know we're looking at a flat line constant, right? Doesn't always have to be that way where it's doing the same thing all the time. So if you look at this nice little, like this looks like a cubic function. As we move from left to right, over here, right, our derivative is positive. Then we get to the top, our derivative would be 0. Then between here and here, our derivative is going to be negative. And then once we pass this point, our derivative is going to be positive. So the sign of the derivative, whether or not it's positive or negative, tells you everything you need to know about whether or not your function is going up and down, up or down. Agreed? And that brings us to what's called the first derivative test. So it says, suppose that you have a critical number of a function. Do you all remember what critical number means? Suppose C is a critical number of a continuous function. What is critical number? Anywhere the derivative doesn't exist or is 0, right? So let's say you're looking at a point where the derivative is 0 or doesn't exist. If the derivative changes from a positive to a negative at that point, then you're looking at a local maximum. If the derivative changes from a negative to a positive at that point, then you're looking at a local minimum. And if the derivative doesn't change signs, then you're not at a max or a min. So let me show you this visually. Look at this point right here. Local max, right? Local max. So the derivative there is what at this point? 0, okay? The derivative there is 0. But the first derivative test says, God, dang it. First derivative test says that, whoa. Okay, here we go. Why is that not? I don't want that there. Okay, here we go. All right, so the first derivative test says, look, if you have a point where the derivative is 0, which is right here, as I move left to right, my derivative on the left side of it is positive, right? My derivative on the right side of it is negative. So anytime you have a switch from a positive derivative to a negative derivative, as long as that's a critical number, you're looking at a local maximum. Right? What about right here? The derivative here is 0, isn't it? But what's the derivative to the left of it? Negative. What's the derivative to the right of it? Also negative. See how it's negative on both sides? There was no change in sign. And if you don't have a change in sign, it's impossible for you to have a local max or min. You have to have a switching of the derivative from positive to negative or negative to positive. You can see it here. We have a local min, right? So as we move from left to right, our derivative goes from negative to positive, right? So this first derivative test is something that we're going to do in order to find local maximums and local minimums. We're going to look at the critical numbers. We're going to look to the left of it and look at its derivative. We're going to look to the right of it, look at its derivative, and we're going to hope to see a change in sign. Going from plus to minus is a max. Going from minus to plus is a minimum. What this thing does, though, is it talks nothing about closed intervals. Did y'all see that? This is not talking about closed intervals at all. So I told you 4.1 was going to be about trying to find absolute max and mins on closed intervals. And then once we get past that, we'll be looking at trying to find local max and mins on open intervals. And this is going to lead us to that, because there's no condition for closed interval for this. All right? So let's just do an example. Find the local max and mins of, we're going to have to do a real easy one here. Let's find the local max and mins of this function. Notice that that function is not defined on a closed interval, right? So I just want to know, does this thing have any hills or valleys? Can we find any of the hills and valleys on this? Now we actually know this is a parabola, right? Opens which way? Up. So this should have a local minimum, shouldn't it? But will it have a local max? Shouldn't, all right? So let's go through the procedure. First thing we're going to do is we're going to take the derivative. What's the derivative of this function? 2x minus 4. Okay. And now we're going to see where that's 0 and where it's undefined. So where's that thing 0? Okay, so we solve it, right? 2x minus 4 equals 0. We get x is 2. So that's a critical number, right? Now we figure out where's that thing undefined or does not exist. Does the derivative ever not exist? No, it's a nice line, right? So don't worry about that. Okay, so we have a critical number, right? What we just looked at was that if we look at the derivative to the left of this and to the right of this, the sign of that derivative will tell us whether or not we've got a local min or max, right? So the standard procedure here is this. We're going to draw a number line. We're going to put our critical number 2 here. We're going to put a dotted line in between. And then what we're going to do is we're going to pick a point to the left of this and to the right of this. Any point you want. It's up to you. You have some freedom here. I'm going to pick 1. I like to put a little x here. I don't like to put dots, okay? Little x there. Circle it. That's a test point. And then 3 is a nice little test point, right? And what I'm going to do is take these 2 points and plug them into the what? What do you think? I'm interested in knowing if it's going down or up, right? Or up or down. So the derivative tells me that, right? So I'm going to take those points and plug them into the derivative. Okay, into the derivative. So over here, I'm going to do f prime of 1 and f prime of 3. So what is the derivative? What is the value of the derivative at 1? So come over here, plug 1 in here. You get negative 2. But all I care about is what? That it's negative, right? It's negative. So that means over here, to the left of 2, the derivative is negative, which means my original function is going which way? Down. So I like to do this. I like to write f with a little arrow like that. So that just tells me, look, to the left of this dotted, the graph on this side is going down. Make sense? Okay, now check 3. What happens at 3 if you plug 3 into the derivative? Remember, not up here, right here. You get positive 2. And all I care about is that it's positive. So that means at 3, my derivative is positive, which means my function is going up. So since my function goes down and then goes up, and this number is a critical number, right? And that number is actually in the domain of this. Like I can plug 2 into this, right? That means that this is going to have to be, I'm going to have a local minimum here, right? That's going to be a local minimum. So this right here, I have a local min at f of 2. So what I'm doing now is, I'll just do this, not at. I'll put local min, and I'm going to plug 2 into the original function to actually figure out what that value is. So if we plug 2 into that function, I think we get negative 9. Basically, we just found the vertex, okay? I mean, that's what we just did. We just found the vertex. Okay, we will have more of this to come. I think now's a good time. So here's what I'm going to do. We have a little over 15 minutes. I have a quiz for you. Yes.
What problem sets can we get started on?
You can do finish 4.1 if you haven't, and then 4.2. All right, so here's the deal on the quiz. I'll give you two options. Option 1 is you work by yourself, you can use your notes. Option 2 is nothing, no references, nothing at all. No formula sheets, nothing, but you can work together. So, think about it. And when I say work together, I mean like at your table. You can't like go across to other people and, you know. So what do you want? Hurry up, make a decision. How many of you want to work by yourself with your notes? By yourself with your notes. Okay, work together, nothing on the table except the quiz. Is that the way we're going? Pardon? Yeah, I want everyone doing the same thing. So we'll go by majority. One more time. How many of you want to work alone with your notes? Okay, how many of you want to work together with nothing but each other? Okay, we're going to go with that. So you can use your calculator, even though I don't think you'll need it. Other than your calculator, everything else has to go away. Okay, so don't be sitting here going, oh yeah, on that first part, just do this. Talk quietly amongst yourselves. Everyone's turning in their own. And you've got until the end of class, which is 15 minutes from now. I think I owe you one here. There you go. There you go. Enjoy.